Good day, dear friends, dear colleagues. Our next speaker, Daniil Mamaev, St. Petersburg State University. He will talk us about Morse index retrieval. Please, you are welcome.
Thank you. Yeah, first of all, let me thank the organizers for the opportunity to speak at this chamber yet reaching content conference. I will talk about Morse index retrieval, and it's a work in progress on the supervision. Okay. Yeah, and it is a work in progress under supervision of Daniila Panina. The results so far can be found on arXiv. I have the number written somewhere. And I will start by formulating. Can you see what happens here at this side of the? Yeah? Okay, so I will start by formulating the problem. So suppose we have a unit ball and a smaller ball inside it. So we call the smaller ball U, and this area is the unit ball minus a small ball. And we have a function f, a smooth function on this annulus, well, multidimensional annulus to real numbers, smooth function without critical points.
U is open or closed?
Huh?
U is open or closed?
It doesn't really matter. Let's say closed. Yeah, let us consider the space of all extensions of our function small f to the whole unit ball, smooth extensions, such that, well, first they are extensions. Second, they have a unique critical point, which is at the origin. This is the origin. And third, the critical point is non-degenerate. So the form of second derivatives at this point is non-degenerate. And to each such function, there correspond a number, lambda f, the Morse index of the origin with respect to function f. So it's a function from the space of all the extensions to numbers from 0 to n, which I will abbreviate like this. So yeah, and let us consider the set of all the possible indices of the extensions of our function small f. And the problem we are interested in is what the set lambda f can be. So like what subsets of the set from 0 to n can be the sets of indices of the extensions of some function defined in this annulus.
What is n?
Huh? N is the dimension of the ball.
Can the index be larger than the dimension?
No, it's from 0 to
Oh,
n.
yes, it's the index. non-degenerate critical point.
Yes, it's a non-degenerate critical point. Okay, so let us make some simple observations. First, let us know that the parity of the indices of extensions of the same function, they must be the same. So either they are all even or they are all odd. Well, it's easy to see, but let me prove it nonetheless. How you do this? Okay, so first let us pick a metric. Is a remaining metric in the unit ball such that, well, first let's take a function. Then pick a metric such that near the boundary our metric is standard, so like the standard Riemannian metric in Rn, and near the critical point, near the origin, well, as our function is Morse, there exist coordinates x1 to xn such that f is the following quadratic expression. So first you have lambda negative squares, then you have the rest are the positive squares, up I from lambda plus 1 to n positive. And you want your metric, besides that the gradient with respect to this metric of your function f is what you would expect the gradient to be. So it's minus 2x1, blah, blah, 2xn. Okay, so you picked a metric. Now, let us look at our function more closely. So in these coordinates, let us consider a small sphere around the origin. It's something like this. It's the sphere, sum of xi square equal to epsilon. And connect the sphere to the exterior sphere by an isotopy. So you connect it, and you get an isotopy from the product of the sphere with the interval to the unit ball. And let's look at the function v equal to the gradient at point h of xt divided over its modulus. Well, it never vanishes since there are no critical points other than the origin. So you get a function. So you get a function from the unit sphere. From the product of the unit sphere and the interval to the unit sphere. And so the degree of this function on the outer sphere is equal to the degree of this function on the inner sphere. But as our function f is just the small f near the boundary, this degree on the left depends only on the initial function small f, only on f. And this thing, well, you have your function is standard in the neighborhood of the origin, and the gradient is standard in the neighborhood of the origin, so you just do the simple computation for this function and this gradient vector field, and you get that this degree is equal to the minus n to the power n plus the index. So you see that, yeah, the parity of the index depends only on the initial function f. Okay. Similarly, you can see that if f can be extended to the unit ball without critical points, then there is no way to extend it with only one critical point. Then lambda f is the empty set. Also, yeah, lambda f can be just a singleton. How to do that? Well, just consider this function. So let f be this function, the standard one. Sorry?
What is f small?
F small is a function in the multidimensional annulus. I don't know how it's, the spherical shell, which is between the unit sphere and the small sphere around the origin. Okay. So, yeah, if your function f is like this, then of course you can just by the same formula. What? Then of course by the same formula you can extend it such that it will have index lambda. So obviously lambda is in lambda f. To prove that no other index can be obtained is, well, it's not very hard, but you need to prove that it's indeed a singleton. You need Morse-Baranikov complex. Morse-Baranikov complexes. So you just look at the canonical form of the corresponding Morse-Baranikov complex, and you see that indeed the function can be extended in any different way other than with index lambda. I will probably speak about Morse-Baranikov complexes in some details later. Okay, now the main result. The main result is that for any dimension, which is at least 2, and for any lambda, the index from 0 to n minus 2, there exists a function small f such that the set of possible indices of its extensions consists of exactly 2 indices, lambda and lambda plus 2. And yeah, let me give a sketch of the proof. In dimension 2, yeah. So you basically apply some theory to construct such function. So you start.
So then, if n equals 2, then you're going to construct a function with 2 different extensions. One with minimum at
Yeah.
0 and
Another,
the maximum
yes.
0 without other critical points.
Yes.
Interesting. Okay.
Okay. Yeah, so yeah, in 2 dimensions, yeah, the question is basically like, suppose you are wandering in a fog, and the question is whether you can tell a mountain from a crater by wandering around. And the theorem says you that, well, not necessarily. In some cases, for some types of landscape, you cannot tell crater from a mountain. Okay, so let us start with a function of two variables, which is simply the height function, the second coordinate. So there are two critical points. Yeah, and let's look at its restriction to the unit sphere. There are only two critical points, the North Pole and the North Pole and the South Pole, and the gradient points up at both of these points. Okay, now let us transform the circle into the following figure. Not changing the function. The function is still the second coordinate. So you look at this figure and you see that there are four critical points now. The gradient still points up at each of them. Okay, it was one way to transform our circle, and the other way is to do it like this. So, yeah, still four critical points, but now, well, here the gradient it points out at the newly created critical points, and here it points in. Okay, now let me take some colored chalk. Yeah, and let us put a point of maximum here. So and change the curve. So what you do is you take a point of maximum. So everything points to this point, at least in some neighborhood. And in this fashion, we exchange this critical point for this critical point. And what's the difference between this one and that one is that at this critical point, the gradient points out, and at this critical point, it points in. And similarly, and here, let me also write what is minimum and maximum. So here is local minimum, local maximum, local minimum, local maximum, local minimum, local maximum, local minimum, local maximum, local minimum, and we inserted a point of index 2, right? And at the lower picture, let's insert a local minimum. So a point of index 0, and you replace a critical point with the gradient pointing in, the critical point with the gradient pointing out. Still a local minimum. There's still a local maximum. Okay, let us now do a diffeomorphism of the picture so that the inserted critical points go to the origin and the curve is just the circle.
Well, I don't get it. If the gradient goes down, then wouldn't local minima turn to local maximum?
No. Why would it? I mean, like here, it goes in this way.
You originally the gradients go out, but then you add this red piece, and on the top of the red piece, the gradient is pointing down.
Mm-hmm. Yeah. Okay. So, well, in fact,
it looks like on the top picture, the top red point is the local minimum, because the direction where it grows, it's kind of.
well, it's not.
No, okay.
I mean.
Well,
Well, in fact, like you can do this in such a way that your function, like your function at this piece and at this piece, is the same. So yeah, well, you can.
You mentioned that this is Baranico string. Just you should refer. It is Baranico string, isn't it?
Yeah, it's a lemma by Baranikov, I guess. Yeah, it's. Barannikov 94. Yes, sorry for not mentioning him yet. I will do this lots of times later. Yeah, so now.
The function doesn't change. The function of the circle doesn't change.
But the extension to the neighborhood changes, right?
Yes, of course.
Oh, yes. I see what you mean, yeah.
Like, yeah.
I see what you mean.
Okay, so now you do a diffeomorphism and you place the critical points into the origin, and, well, let's say you put your critical points of the restriction like this, so it's 1, 0, 1, 0, 0, 1, 0, and the gradient points first 2 times out, then 2 times in. So these 2 functions, they look quite similar near the boundary, but, well, they're not the same. There is no reason for them to be the same. So to actually construct a function that can be extended in 2 different ways, with index 0 and index 2, you need a further step, and this is the following. Let us put these circles concentrically like this. So, yeah, let it be, well, this is the unit sphere, this is half of the unit sphere. And inside the smaller ball, yeah, let us denote this function by f2 and this function by f0. So inside the smaller ball, we have the function f2. And near the boundary of the larger ball, we have the function f0. Well, not quite. First, it's not f2, but f2 composed with something like 2 multiplied by something. And second of all, f0, we replace it with a composition of some diffeomorphism such that the values at the corresponding critical points are coherent with the gradients. So here we want the value to be smaller than here. Here the value should be larger. Here the value should be larger again, and here it should be larger is this way, and this way, yeah. And here it should be smaller. Okay, so L is a diffeomorphism of the real line, making this function f0, well, just shrinking it this and that way. And yeah, so, and it turns out that if we have such a picture, and we can actually find a function g, such that a function g from the unit ball to R, such that near the boundary it agrees with function f with our modified function that can be extended with index 0, and near, well, not near, but in the smaller ball, it agrees with, well, the function f2, well, modified slightly. And, well, we are done. Then, well, it's a smooth function. So, yeah, let's take small f to be g restricted to some thin layer near the unit sphere. So something like Well, I don't know. And then if you take the extension of f small to be g, then it has index 2 at the origin. And as g agrees with, so it's the same thing as L composed with f0 near the boundary. And this function can be, well, it has the critical point of index 0 at the origin. So we are done. That was the sketch in the two-dimensional case, and let me comment a little bit about what we should do in high dimensions. So, yeah, first step. Yeah, first of all, well, you can't really draw these pictures in high dimensions, so you should insert your points like by simply writing formulas. And for this all to work, you need to insert this pair of points and this pair of points on the same gradient line. So, well, here in two-dimensional case, there is only one gradient, well, two of them, but yeah, well, they are on the same gradient line, going from this global minimum to this global maximum. And in the multi-dimensional case, you should keep it this way. Then, while inserting of critical points, yeah, you can also do that. Yeah, and you want your function, the restriction of your function to the boundary to remain the same. You can do that. Then you don't need this step because you never changed your boundary. You were changing the curve. And yeah, also when inserting this pair and this pair, you should make sure that the gradient lines they remain like similar. That the picture of inserting, like you inserted somewhere here two critical points and somewhere here two critical points, and well, and you have like gradient line that goes like this. So yeah, well, this picture should map to this picture under the flow generated by the gradient lines. Well, you can do that. And yeah, don't need this step. And this, well, yeah, you do basically the same, and you can connect function f lambda and f lambda plus 2 exactly because there is, well, there is a single vector field for them, such that these functions, the derivatives of these functions along this field are positive away from the critical points. Yeah, that's pretty much it about the proof. I'm sorry, we only proved that for this function f, we proved that lambda and lambda plus 2 indeed can be the indices of some extensions. And to prove that there are no other indices, you need Morse-Baranikov complexes, and that's what I'm going to talk about now. I don't have much time, so I will try to be brief. So Morse, Baranikov complexes, and from now on, pretty much everything I say is written in the paper by Baranikov. So I will just reproduce it. Okay, so suppose you have a function f in a neighborhood of the unit sphere, and let's note by small f its restriction to the unit sphere. And yeah, let's say that there are no critical points of the function large f at the unit sphere. so df never vanishes on the unit sphere. And let us pick a metric such that, well, a good metric, such that the ascending and descending manifolds for the function small f on the unit sphere, they all intersect transversely for different critical points. And the Morse Baronic complex is the following picture. First, you draw a number of lines, well, n plus 1, n of them. Then for each critical point, I should probably go to some other blackboard. I will this one. So yeah, if you have a critical point of the function on the unit sphere, then you put a vertex with coordinates, well, first the Morse index of this point, and the vertical coordinate is the value of the function at this point. And if you have, well, you look at the usually defined differential in the Morse complex. So it's some linear combinations of critical points of index 1 less. Yeah, and this coefficient is just the signed number of gradient lines from, where do they go, from P to Qi. And so, yeah, if differential of your point P is this linear combination, so this is lambda P, this is lambda P minus 1. Your points, let us number them in the order of increasing of the value of the function at these points, Qm. Well, there might be some others. This is point P, so you draw edges with labels equal to the coefficient at the corresponding critical point. Of course, if the coefficient is 0, we don't draw any edge, and we don't write a number if it's equal to 1, and so on. So let me illustrate it on this picture. So here, only two critical points. One is the minimum, one is the maximum. And so it's like this. And also, on the Morse-Barennikov complex, you indicate where the gradient points. So if gradient of function f at point P points out, then you put an arrow up. If it points in, you put an arrow down. So in this example, here it points out, so the arrow goes up. Here it points in, so the arrow goes down. Now what happens here is that you insert two critical points. And both of the gradients, they point in. So your picture is like this. Well, there are 4 gradient lines. And some of them have negative signs, so I guess this should be -1, this should be -1. And for the upper picture, the Morse-Barennikov complex looks like this. You put 2 new critical points and both the gradients point out. And again, you have all the 4 gradient lines. After changing it, what happens is that you change the direction of one arrow, and here you change the direction of this arrow from down to up, here from down to up. And here you change the direction of one point from up to down. So from up to down. Okay. Yeah, well, this doesn't change anything. Yeah, that's it. And we see that in our transformations, the Morse-Baraniuk complex changes somehow, and in fact, it changes in a very particular way. So if you know some search theory, then you know that any two Morse functions can be connected by a path, such that all the functions in this path are either Morse functions or functions having a singularity with, well, such that the matrix of second derivatives is degenerate, but degenerate only in one direction. And so that's what happens if you pass along your path connecting to your functions through a function with this simple singularity, then you add or delete 2 critical points, and it turns out that you can only add or delete 2 critical points with the same direction of arrows. And if you like changing your function in such a way that it remains Morse, then you only move the values at the critical points, and these values, they move in the direction of the arrows. And that's basically it. That's all the possibilities you can have if you do not meet a critical point of the function, like of the whole function, which is defined in the whole ball. And if you pass through such a critical point, as Baraniuk proved, you can indeed do it in such a way that just direction of one arrow changes. And it can change. So here we pass through a critical point of index 0, and it changes from up to down. And indeed, for index lambda, we can have on the level lambda a change from up to down. And here in the upper picture, the index of the point we pass through is 2, and we change a point of index 1. So yeah, the other possibility is that on the level lambda minus 1, we change the arrow from down to up. And that's it. There are no other possibilities to come through a point of index lambda. Yeah, and then by carefully analyzing what can happen in these pictures, and also introducing so-called canonical forms, so like further simplifying these pictures, you get abstractions to the possibility to exchange your function to the unit ball in some way. I mean, because, well, okay, yes, if I have one more minute. Okay, thank you. So you have your function near your unit sphere. You have one critical point. Let's look at the small sphere here, and let's look how the function changes when we go from the smaller sphere to the larger sphere. And yeah, as we know, how Morse-Barnikov complex can change by when we go from the small sphere to the larger sphere, we obtain some abstractions to the existence of such a function. And that's how you prove that in this case you have only one Morse index, and in the main result there are indeed no other indices but lambda and lambda plus 2, such that the function f can be extended with these indices. Thank you.
Okay, thank you very much.
Do you have examples where this set is bigger than 2 elements?
No, not yet.
Not yet. Okay, thank you.
Yeah, but like if you look at the Morse-Barnikov complexes, then like there are some metamorphoses of them that like allow you to get more than 2 different indices. But unfortunately, these metamorphoses are not, they can't be realized geometrically. So, yeah. But I don't know whether it's not possible at all, or I'm just, haven't found yet the right metamorphosis of the Morse-Barnikov complex.